Okay, we're gonna talk a little bit about rational functions. We talked quite a bit about polynomials and how they occur. And rational functions can be understood in a way very similar to the way we understand just any old polynomial. So as an example, let's say we have the polynomial okay, this is a polynomial in factored form, and this is a very simple degree one polynomial. Okay, it's a linear expression, but it's still a polynomial. It's power of x and a number. Okay. So what do we know about the graph of this thing? Well, first of all, and I'm kind of using front notation. So I'm going to change the word graph. The function has zeros where the numerator is 0. As long as the denominator doesn't have the same 0. Okay. Now the numerator is 0. You have x minus 1 times x plus 3 squared equals 0. We note that we have a simple 0 if x equals 1, because if x equals 1, the whole thing is 0. And zero multiplicity 2, if x equals -3. As we saw last time, multiplicity 2 really tells you that the thing acts like a parabola in the immediate vicinity, because x plus 3 squared is just your toolkit squaring function shifted 3 units to the left. Okay. And we'll say more about that maybe, but that's what it comes down to. And this is just like a linear function. X minus 1 is just a linear function. So the graph passes through that linear 0. It's basically something very close to a straight line. So if you want to understand the shapes of graphs, what I just said is pretty important, and we talked about it last time. Okay. So we already know some things about the graph. And rather than trying to crowd the whole thing onto one board, I'll come over here and start constructing the graph. So here's a graph. And we have a simple 0 at x equals 1, 0 multiplicity 2 at x equals -3. So I'm going to put -3 about here. X equals 1 here. And I note that this 0 at x equals -3 has multiplicity 2. So that when we hit the 0, if we're coming in from above, it's going to be shaped like this. It's going to be a parabola opening upward at this case point. Now, it's not going to stay a parabola, but it's going to be very close to a parabola if you're very close to this point. So it's going to have a shape like this, or if you're coming in from below, it's going to have a shape like this. So it's either going to be an upward opening parabola or a lower opening parabola in the immediate vicinity of this point, and this point is going to be a vertex. This is a simple 0 of multiplicity 1, and you're going to go through this 0 either up or down, either with an upward slope or downward slope. So we know that much about the graph. We also know the y-intercept, which we find in the usual manner. And that's going to give us -9/8. So let's just say this is the line. Y equals -9/8. The 0 is right there. Or the y-intercept, I'm sorry. So that 0 is here and here. This 0 is going to be quadratic. It's going to be parabolic in shape. This 0 is linear. It's going to be nearly a straight line in shape. We've got to go through this point. Now there's more to it. Denominator goes to 0, it is 0. If x minus 8 equals 0, so it's happens at x equals 8. So let's put x equals 8 out here. Okay. Near 0 at x equals -3. What is the graph? Well, okay, back up a second. I'm not sure I want to go there just yet, so I'm going to stick with what I'm doing. Okay. If x is close to -3, I plug in -3 for every x except the one that gives us the 0. Okay. And then you can evaluate this. That's -4, that's -11. Like 4/11 times x plus 3 squared. Now, between, let's say, here and here on this short interval, x stays close to 3. So that the value of the quadratic function stays close to 4/11 of x plus 3 squared. If we put in a number close to 3 here and here, we're still going to get something pretty close to 4/11. Okay, as long as we stay very close, this fraction isn't going to change much. And this is just vertically compressed toolkit squaring function shifted 3 units to the left. So what we get is something that looks maybe kind of like this. The values of x that are very close to x equals -3, we're going to have something very much like a parabola. Now close to x equals 1. Well, x is 1. 1 and 3 is 4, and you square that, you get 16. And then 1 minus 8 is -7. Close to -16/7 of x minus 1. And a graph of -16/7 times x minus 1 is going to have a slope of -16/7, and it's going to pass through this point. So according to the scale of the graph, well, I'm not going into too much detail. I've got a problem here. I'm seeing a potential problem, but anyhow, the graph should be going through this point, something like this. Now, there's a problem with that because the graph isn't behaving like we would expect. Oh, when I said the y-intercept was -9/8, I was wrong, because we have a negative here and a negative here, and this is positive, it's plus 9/8. So turns out the y-intercept isn't here. Clean that up a little bit. I was careless with my signs. Graph goes through this point. The reason I know the graph can't go through here is it's got to be like this at this 0. It's got to open upward. So there's no way for it to get from this 0, go down through here and get through this 0 without going through the x-axis again. Okay, and it can only go through the x-axis at zeros. So that wasn't going to work. We'll sketch a couple out and see just how that sort of thing works. But if you don't get your points in the right place, you're not going to be able to draw the curve right. Okay, so far we know that the graph is going to kind of do this here. It's going to kind of do this here, meaning we can pretty much sketch what we think the graph might do. Comes up here, then it's got to turn around here, and it goes through here with about this slope. That makes sense? Now that much you could do with just a polynomial. But we have a rational function that has a 0 to the denominator at x equals 8. So let's see what happens near x equals 8. Well, if I plug 8 in for all the x's except the one that would give us a 0 here, we're going to get 8 minus 1 times 8 plus 3 squared over x minus 8. And that equals, that's 7, and that's 121. And 121 times 7 is 847. So what we have is, first of all, the reciprocal function, the 1 over x function, vertically stretched by a factor of 847. It really stretches it out, okay? And then shifted to the right 8 units. And I've got another small problem here. Because, no, never mind. Thought I had a problem, but I didn't. Okay. So there we have this function. Now, what's that function look like? Well, this function looks something like this. Goes down here, comes down from here, just like the reciprocal function. Okay. So what you get is this thing just takes a dive down here, and it's going to be an asymptote to x equals 8. On the other side is going to do the same sort of thing. It's going to come down like this. And there's a large part of your graph. The other thing we have to figure out is what the long run behavior is. Now, open math tells you use big numbers and convince yourself, and that's fine. But I think it's actually easier if you understand the toolkit functions. And not sure everything I wrote there is pretty much visible, but I move this board over a little bit. I was going to use this space. It's going to take more room than that somewhere. You think that? Okay. So what we have so far. Got this function. We call this R of x a rational function. The numerator is 0 at 1 and -3, and that's going to give you zeros just like a polynomial would. Then you have the reciprocal of x minus 8 there. The reciprocal of x minus 8 is a 1 over x function shifted 8 units to the right. That's going to be multiplied by whatever the value of this junk here is, okay? When x equals 8. Or when x is close to 8, and that's going to be close to 847 over x minus 8. X is close to 8, this is close to 847, and then you have the x minus 8 in the denominator. All right. you can look at this polynomial, if you multiply it out, okay? You can square this, you get x squared plus 6x plus 9. Then you can multiply through by the x and by the minus 1. That's going to give you x cubed. And then you're going to have 5x squared. And then you're going to have 9x and 6x is 3x minus 9 over x minus 8. If you do long division, you're going to get an x squared here. You're going to get an x cubed minus 8x. A little plus sign there and a little minus sign there to remind what you're doing. And you're going to have then 13x. Whoops, wait a minute. Yeah, it's 8x squared. Okay, you're going to have 13x squared plus 3x. That's going to give you 13x. That's going to give you 13x squared minus 84, 104 x. A little plus there, a little minus there to remind yourself. And you have then 107x minus 9. So that would be plus 107. And then you multiply that through, you get 107x minus 872. That's going to actually be added, that's going to be subtracted, and you get 881. Okay, well, then you could write that as plus 881 over x minus 8. So that's long division, which I assume everybody either knows or can get confident with. My point is not so much all this stuff, although it's important and I'll mention it. The point is that if x is really big, then it's 881 over x minus 8 is 881 divided by something really big. It doesn't amount to much. Like if x is 1,000,000, you have basically 881 over 1,000,000, which is 0.0008. 9, if you want round off, it doesn't matter. But this becomes insignificant. So does 107. And so for the so does a 13x. Large x, everything but x squared becomes insignificant. Compared to x squared. And the graph is almost just like y equals x squared. For large x. This means that the graph looks like this. It's just like the graph of x squared. Okay? Except that in near the y-axis, it can wiggle a little bit, and it can even have an asymptote. Okay? So in green here, I just marked a little wavy line, then I marked a vertical line to indicate you could have an asymptote. So if you look at this thing from far, far away, this is what it looks like, and you just got this little stuff in here you can barely see. Well, how does that fit in this picture? Well, it tells you that as soon as you get away from this region between the zeros and the asymptote, x is just going to go on up like that, like a parabola. I'm sorry, your graph is going to go on up like that, like a parabola. And to the right of this point, things going to turn around and just take off, go up like a parabola. They have rules for that. And, you know, I'm just not completely satisfied with the way the long run behavior is often presented. Because it's easy enough to understand this if you know the toolkit functions. It's easy to understand that if you do this division, you're going to end up with an x squared, and the graph is going to be like x squared. Okay. But in closer to the origin, it's going to deviate from that. In fact, it's going to deviate like crazy. So let's just reconstruct this graph using that information. Okay, so here we are. And we have the line x equals 8, which I'm going to put in about here so we can go out into some larger values of x. And then we have x equals -3 here. And x equals 1 here. And we have y equals 9/8 here. We're going to go through this point, we're going to go through this point, we're going to go through this point. This point comes about because of the x plus 3 squared. So the graph is going to act like a squaring function here. Overall, you've got this parabola. Okay, so I'm going to draw the parabola. In blue, so here comes your parabola. Okay. Big old parabola. Just the x squared parabola. Now the scale isn't quite right. So probably the parabola would be much steeper. So we're just kind of getting a schematic here. Like when x equals 8, this parabola would be up at 64, which would be up to the ceiling someplace. So it's much steeper parabola. Still, you get the idea if you just kind of say, okay, it's overall it's a parabola. So what you do is your graph stays with this parabola until you get down to this point, and then it gets a little bit of a parabola at this 0, just like we did previously. That comes up here, so it can come down through this point. And then I put an x at this point. I probably shouldn't have. I'm just going to make that vertical line. I'm going to make that vertical line a little more solid. And then we just go down here. And over here, we come down from this asymptote for ways, and then we turn around and follow the parabola. And that's what the graph looks like. It's following the parabola. It gets a little ways away from this region on this side and on this side. Okay. So you say the long run behavior is Well, it's gonna go up like this, it's gonna go up like this. Why does it go up like that? There's a rule for it, and you can use that rule. I'm sure you'd be fine if you just use the rule. But there's a reason for the rule. And you get the reason if you understand the toolkit functions and the shapes. And understand that their toolkit functions just hidden in this function. Right there's the function. You got a parabola with a vertex at 0 and -3. It's just a parabola for a short time. You know, this thing doesn't stay a parabola because it's got to twist around and go through this point. It doesn't stay a parabola here. It joins up with a steeper parabola. Okay. So it's a distorted parabola, but if you look very close in this very small region and zoom in on it, it'll look almost like an exact parabola. That's because of the x plus 3 squared. The x minus 1 gives you almost a straight line as it goes through x equals 1. And apparently I'm going to do really dumb things today because, of course, the graph should have gone through this point. That's your y-intercept, and it should have gone through this point. Okay, so I just wasn't looking carefully when I made those points, and obviously wasn't thinking straight. So let me just fix that a little bit. And we go through this point, and we go through this point. We got to come up here, so we go down through this point, get down through this point, and then we follow an asymptote to this line. Looks very similar to what we just had, but it's now correct. We didn't have a point right here. That was ridiculous. Okay. Again, you go through this 0. It corresponds to x minus 1 on a straight line because x minus 1 is a linear function. Then you have the x minus 8 here in the denominator. So that's like a reciprocal x. It's like 1 over x minus 8 times all the rest of this stuff. And, you know, 1 over x minus 8 is the horizontal shift of 1 over x. So it's like you have your toolkit reciprocal function, the shape of the toolkit reciprocal function close to this asymptote. Doesn't stay close to the asymptote. You know, the toolkit reciprocal function shifted over here to give you something like this. You have an asymptote at the x-axis in here. It doesn't go to the x-axis because it's got to follow that big parabola as you get away from this region. So, that make any sense? There's reason for the rules, but the rules say find the zeros in the numerator. Those are going to be 0. Look at the multiplicity. That'll tell you whether it goes straight through or acts like a parabola or acts like a cubing function or some other power. The denominator, you're going to have like reciprocal functions. And reciprocal functions have asymptotes at the y-axis. If you shift 8 units to the right, which is what you get, you know, 1 over x becomes 1 over x minus 8, that's going to shift the graph of 1 over x 8 units to the right. That should be familiar. And if it is, then you get a good understanding of the whole picture. There's more to the rules than that, but that's the basis. It's a basic thing you need to understand about rational functions. Zeros of the numerator give you real zeros in the numerator, give you intercepts with the x-axis. Real zeros of the denominator give you vertical asymptotes. Now, sometimes you could have an x minus 8 here and an x minus 8 up here. Okay. In that case, 8 would not be in the domain of the function because you can't have 0 in the denominator. But since there's an x minus 8 up here, you can divide this into that, and this one goes away. So does that one. Okay. Call that a removable singularity. You've seen that, haven't you? Okay. So I'm not going to do an example of that. I want to give you the overview as best I can without getting mixed up in all the little rules, but the little rules just come right out of these ideas. So let me give you one CD graphic. Leave all this stuff up here. Let's just say it's I don't like that. I've got x minus 5, and x plus 7. Can you read it? It's kind of smudged. We'll clean it up in a minute, but just copy it down and see what you can figure out. Okay, very quickly, we're going to need to graph this for 2 minutes over time, so I'm going to do this real quickly. Numerator 0. X plus 4 times x minus 2 equals 0. So x plus 4 equals 0, or x minus 2 equals 0. You solve this, you get x equals -4. You solve this, you get x equals 2. So here's your graph. X equals -4. X equals 2. The numerator is 0. If the numerator is 0, the whole thing is 0. As long as the denominator isn't 0. So we have these 2 points. Y-intercept. You get 0 plus 4 times 0 minus 2 over 0 minus 5 times 0 plus 7. And that equals, and oh, this was cubed, incidentally, cubed. So the fact that it's x minus 2 cubed equals 0 means you have degree 3. Okay. Or multiplicity 3. Okay, you do this and you get 32 over 35. There's your y-intercept. So at y equals 32 over 35, you get the y-axis. Graph has to go through this, this, and this. Here, the degree is 3. Okay, now denominator equals 0. X minus pi times x plus 7 equals 0. This splits into 2 equations. X minus 5 equals 0, or x plus 7 equals 0. The solution, x equals 5, or x equals -7. And as I've emphasized, write out the equations, write this out. Because if these are more complicated expressions, you're going to have to understand that you have equations to solve. And solve this equation. Add 5 to both sides, you're going to get x equals 5, right? Add -7 to both sides, you're going to get x equals -7. Do the actual math instead of just spotting it, okay? Although it's easy to spot, and that's okay. You should understand, and when you're starting out, do all the math. Write out every step, don't skip anything, so that you can put this whole thing together and do it efficiently. Okay, so there we have all this. Now, so graph is kind of like 1 over x minus 5, but with a vertical stretch. So we come out here to x equals 5. And we'll kind of darken that line to make sure we understand it's an asymptote and not just a projection line. Okay, and similarly, it's like a stretch 1 over x plus 7. Now, you should know that 1 over x minus 5 is like 1 over x shifted 5 units. If you don't know that, review section 2, 1.2, I think it is, where it introduces the main functions, okay? Because those functions are what the course is all about. It's built on those functions. You gotta know those functions. Okay, here's mark up, you can get that. So make sure you do. Okay, near x equals -7 is like this. So here's, let's say this is x equals -7. It's a vertical asymptote. Now, the long run behavior, it's like you got a 4th degree here and a 2nd degree here, so it's like the squaring function. Again, long run. If you expand this and do a long division, the first term you're going to get is x squared. So that means it's got to go up like this and up like this. The reciprocal function then I haven't left myself room to turn around, so I'm going to have to do a quick turnaround. It's not going to go quite this quick. It's going to come down like a reciprocal function. Here it's going to come up like a reciprocal function. Then it's going to turn around suddenly and go up. It's going to do something like this over here. It's not well drawn, but that's kind of what it does. Here you have a 0 of multiplicity 1. This one is multiplicity 3. Multiplicity 1, you go straight through, you go on up here and come down here, and you act like the cubic function, and then you go down to your asymptote. You come down from the asymptote here and go back up. Okay. Now, there's a lot more explanation that we had earlier, but we do have to let my next class in, so I'm going to have to stop here.